There is a galaxy in the deepest regions of space that should not exist, not because it is strange, not because it defies one small detail of our models, but because according to everything we understand about how the universe works, there was not enough time for it to form, not enough generations of stars to create the elements it contains, not enough gravitational collapse to build the structures we observe. Yet it exists. We can see it, photograph it, measure its light spectrum, analyze its composition, and every measurement confirms what should be impossible. This is MOM Z14, one of the most distant galaxies ever observed. Its light has traveled for 13.52 billion years to reach us. We are seeing it as it was just 280 million years after the Big Bang, when the universe was less than 2% of its current age, when, according to our theories, galaxies should be small, primitive, chaotic clouds of the simplest elements, hydrogen and helium. The first generation of stars barely beginning to form. No heavy elements yet. No complex chemistry. No nitrogen or oxygen or carbon in significant quantities. Those elements require multiple generations of stars, billions of years of stellar evolution. Stars forming, burning, exploding, seeding space with heavier elements, and the cycle repeating many times. This is what our theories predict. This is what should be true in the early universe. But MOMS 14 contains nitrogen, lots of nitrogen, 10 times more than it should have at that cosmic epoch. And nitrogen is not a first-generation element. It is created inside massive stars through nuclear fusion, released when those stars explode as supernovas, incorporated into second and third generation stars. This process takes time, billions of years. Yet MOMS 14 shows advanced chemical enrichment when the universe was barely 280 million years old. This galaxy is not supposed to exist as we observe it, and it is not alone. The James Webb Space Telescope has been finding impossible galaxies since it began operations. Too many massive galaxies, too early, too mature, too fast, too organized, when chaos should dominate. Each discovery challenges our understanding, forces revision of established theories, pushes back the timeline of when structure could form, and raises the disturbing question: if our most fundamental theories about galaxy formation are wrong, what else have we misunderstood about the universe? Begin with the discovery itself. January 2026. The James Webb Space Telescope, humanity's most powerful astronomical instrument, was conducting deep field observations, pointing at seemingly empty patches of sky and staring for hours, days, collecting every photon from the most distant sources. JWST is designed specifically for this. Its massive 6.5-meter mirror collects infrared light, wavelengths longer than visible light, and this is crucial because as light travels across billions of light years of expanding space, it gets stretched, redshifted. Light that left distant galaxies as visible blue and green arrives at Earth as infrared. The farther the source, the more extreme the redshift. The most distant objects are invisible to optical telescopes. Only infrared instruments, like JWST, can detect them. And what JWST found was a galaxy with a redshift of approximately Z equals 14. This is extraordinary. Redshift is measure of how much the universe has expanded since light was emitted. Higher redshift means greater distance and earlier time. The most distant galaxies confirmed before JWST had redshifts around Z equals 10 or 11. Finding a galaxy at Z equals 14 pushes observation back to 280 million years after the Big Bang, into the cosmic dawn, the era when the first galaxies were forming, when the universe was emerging from the Dark Ages, the period after the Big Bang, when no stars yet existed, and the universe was filled with neutral hydrogen gas that absorbed all light. The galaxy was designated MOMS 14, part of the JWST Advanced Deep Extragalactic Survey. Initially, it appeared as faint red dot, almost invisible. But when astronomers analyzed its spectrum, the breakdown of light into component wavelengths, they found something shocking. The spectrum showed emission lines, bright narrow peaks at specific wavelengths corresponding to elements being excited and emitting light, and one of those lines was nitrogen. Specifically, the doubly ionized nitrogen line at 205 nanometers in the rest frame, observed at much longer wavelength due to redshift. This nitrogen line was strong, prominent, much stronger than expected. When astronomers calculated the abundance of nitrogen relative to oxygen and other elements, they found nitrogen was overabundant by a factor of 10 compared to what models predict for such an early galaxy. This is the anomaly, the impossibility, because nitrogen should not exist in such quantities so early in cosmic history. To understand why this is impossible, you must understand stellar nucleosynthesis. The Big Bang created only the lightest elements, roughly 75% hydrogen and 25% helium, with traces of lithium and beryllium. That is all. Every other element in the periodic table was created inside stars. Stars are fusion reactors. In their cores, hydrogen fuses into helium. This releases energy that makes stars shine. But massive stars do not stop at helium. As they age and exhaust hydrogen in the core, they compress and heat until helium begins fusing into carbon and oxygen. Then carbon fuses into neon and magnesium, then oxygen into silicon and sulfur, then silicon into iron. Each stage requires higher temperatures. Each stage lasts shorter time. The final stages, silicon fusion, creating iron, last only days, and then the star explodes. Supernovae. The explosion creates even heavier elements through rapid neutron capture, and it disperses all these newly created elements into space. The remnants mix with interstellar gas, form new stars. These second-generation stars are enriched with heavy elements from previous generations, and when they explode, they add more. The cycle continues, each generation increasing the metallicity, the abundance of elements heavier than hydrogen and helium. Nitrogen is created primarily in intermediate mass stars through a process called the CNO cycle, carbon-nitrogen-oxygen cycle. Carbon captures protons, transmutes to nitrogen, then oxygen, then back to carbon. Some nitrogen escapes this cycle and accumulates. When the star ends its life, it ejects this nitrogen into space. But this process requires time. The star must live long enough to produce significant nitrogen, then die. Then the nitrogen must be incorporated into new stars. This cycle takes hundreds of millions to billions of years. In the early universe, at 280 million years after the Big Bang, this process should barely have started. The first generation of stars would just be dying. Perhaps some second-generation stars are forming, but nitrogen abundance should be very low. Perhaps 1/10 or 1/100th the levels we see in the present-day universe. Yet, MOMZ14 shows nitrogen levels comparable to much later epochs, 10 times higher than predicted. This suggests either the models are wrong about how nitrogen forms, or the models are wrong about the timeline of stellar evolution, or something very unusual happened in this galaxy that accelerated the enrichment process beyond what we understand. Astronomers have proposed several explanations, none fully satisfactory. First possibility, the galaxy contains population 3 stars. These are theoretical first-generation stars, never observed. Predicted to be extremely massive, hundreds of times the mass of the Sunday, they would burn very hot and very fast, live only a few million years. And when they explode, they would enrich the surrounding gas dramatically. Perhaps population 3 stars can produce nitrogen more efficiently than models predict. Perhaps their explosion mechanisms are different. Perhaps they seed their environments faster than we calculate, but this requires population 3 stars to exist in large numbers, and to have very different properties than current theoretical models suggest. We have no direct evidence for any of this. Second possibility, the galaxy experienced very rapid star formation. If stars form in enormous bursts rather than gradually, perhaps multiple generations can occur within short time. The first stars form, explode within a few million years, and immediately second-generation stars form from the enriched gas. Then they explode, and third-generation stars form even faster. This kind of rapid cycling could compress what normally takes billions of years into hundreds of millions, but this requires star formation rates far beyond what we observe in local galaxies, and it requires efficiency that seems implausible given the conditions in the early universe. Third possibility, our models of nitrogen production are wrong. Perhaps nitrogen is created through different processes than we think. Perhaps there are nucleosynthesis pathways we do not understand. Perhaps in the extreme conditions of the early universe, different temperatures, different densities, different radiation fields, elements form differently than in the present-day universe. This would be revolutionary, would require rewriting stellar physics, but it cannot be dismissed. The early universe was very different. Perhaps chemistry worked differently. Fourth possibility, we are misinterpreting the observations. Perhaps what we think is nitrogen is actually something else. Perhaps the spectrum is contaminated. Perhaps the redshift measurement is wrong and the galaxy is not as distant as we think. But the observations have been checked and rechecked. Multiple independent analyses confirm the redshift. The nitrogen line is clear and unambiguous. The measurements are robust. So while observational error is always possible, it seems unlikely in this case. The anomaly is real. But MOMZ14 is not an isolated case. This is what makes the situation more serious. JWST has been finding massive, mature galaxies throughout the early universe. Galaxies that should not exist according to standard galaxy formation theory. In the first year of JWST operations, astronomers discovered dozens of galaxies at redshifts between Z equals 10 and Z equals 13. Many of these galaxies are surprisingly massive. Some contain as much mass as the Milky Way, but they exist when the universe is less than 500 million years old. The problem is that galaxies form through hierarchical structure formation. Small fluctuations in the density of matter after the Big Bang grow over time through gravity. Denser regions attract more matter, collapse into dark matter halos. Gas falls into these halos, forms stars. Small galaxies merge to form larger galaxies. This process is gradual, takes billions of years. Simulations of galaxy formation predict that at 300 to 500 million years after the Big Bang, galaxies should be small, perhaps a few hundred million solar masses, not billions of solar masses like the Milky Way. Yet JWST finds massive galaxies everywhere in the early universe. Too many, too massive, too soon. Some astronomers are calling this the JWST crisis in cosmology, not because JWST is wrong, but because JWST is showing us that our models of how the universe evolved are inadequate. The standard lambda CDM cosmological model, cold dark matter plus dark energy, has been incredibly successful at explaining large-scale structure of the universe. Cosmic microwave background, expansion rate, distribution of galaxies. It fits almost all observations beautifully. But it predicts galaxy formation should be gradual and hierarchical. Small structures forming first, merging into larger structures over billions of years. JWST observations challenge this, show that large structures existed much earlier than the model predicts. This does not mean the model is completely wrong, but it means something important is missing. Some process or mechanism that accelerates early galaxy formation. Perhaps dark matter behaves differently than we think at early times. Perhaps star formation was much more efficient in the early universe. Perhaps gas cooling and collapse happened faster. Perhaps there are feedback mechanisms we do not understand that trigger rapid bursts of star formation in the first few 100 million years. We do not know. And this is exciting, because it means we are discovering something genuinely new, something that will require new physics or new understanding to explain. This is how science progresses, not smoothly, not by gradually filling in details of a complete picture, but by encountering anomalies, observations that do not fit, impossible data that forces revision of theories. The history of astronomy is full of impossible discoveries that eventually became accepted reality. In 1929, Edwin Hubble discovered that galaxies are moving away from us. The universe is expanding. This was impossible, according to Einstein's general relativity, as originally formulated. Einstein had added a cosmological constant to his equations, specifically to prevent expansion or contraction. He wanted a static universe. When Hubble showed the universe expands, Einstein called it his biggest blunder. But the universe does not care what Einstein wanted, it expands. And we had to revise our theories. In the 1960s and 70s, Vera Rubin measured rotation curves of galaxies and found they rotate too fast. The visible matter is not enough to hold them together. They should fly apart, but they do not. This led to the hypothesis of dark matter, invisible matter that does not emit light but has gravity, initially dismissed as absurd, now accepted as constituting 85% of all matter in the universe. Another impossible discovery that became foundational. In 1998, astronomers discovered that the expansion of the universe is accelerating, not slowing down as expected. This was so shocking that the discoverers questioned their own data for months before publishing. But the acceleration is real, caused by something called dark energy, an unknown form of energy that fills all of space and pushes everything apart. Dark energy constitutes 68% of all energy in the universe. We have no idea what it is. It was completely unexpected. Impossible, according to prior understanding. Yet it is now a fundamental part of cosmology. Every generation of astronomers encounters impossible observations. Each time, experts resist. Each time, the impossible becomes accepted, and then becomes foundation for next generation's understanding. We should expect this pattern to continue. JWST is showing us impossible galaxies. Eventually we will understand why they exist. We'll modify our theories. We'll accept the new reality. And then the next generation will find something impossible again. This is the cycle. This is how knowledge advances. The nitrogen anomaly in MOMZ14 is particularly interesting because nitrogen is biologically important. It is an essential component of amino acids and proteins and DNA. Life as we know it requires nitrogen. So finding abundant nitrogen in the early universe is not just interesting for stellar physics, it has implications for astrobiology. If nitrogen was available early, perhaps organic chemistry could begin early. Perhaps the building blocks of life formed sooner than we thought. This is speculative. We have no evidence for life at 280 million years after the Big Bang. The universe was still far too hot and chaotic. But it suggests that the chemical prerequisites for life, carbon, nitrogen, oxygen, were available earlier than standard models predict. If galaxy formation happened faster than we thought, if stellar enrichment happened faster, if complex chemistry developed faster, then perhaps the timeline for the origin of life in the universe is different than we assume. Perhaps habitable planets formed earlier. Perhaps life arose earlier in cosmic history. Not in our galaxy necessarily, but somewhere, in some galaxy where conditions were right. This is pure speculation, but JWST is forcing us to reconsider timelines, to question assumptions, to realize that the early universe was more complex and more interesting than we modeled. Another implication of the MOMZ14 discovery is methodological. It shows the power of spectroscopy. Taking a spectrum, analyzing light in detail rather than just taking images, reveals information that images alone cannot provide. The spectrum of MOMS Z14 shows emission lines that identify elements, reveal chemical composition, allow precise redshift determination. Without spectroscopy, MOMS Z14 would be just another faint red dot. Interesting, but not revolutionary. Spectroscopy transforms it into a puzzle, a challenge to our understanding. This is why JWST is equipped with sophisticated spectrographs, instruments that can split light into thousands of wavelengths and measure each precisely. This capability is what makes JWST not just a better Hubble, but a fundamentally different kind of instrument. Hubble took beautiful images. JWST takes beautiful images and detailed spectra. The combination is transformative, allows us to not just see distant objects, but understand them, analyze their chemistry, measure their motion, determine their physical conditions. Spectroscopy is a time machine that tells us not just where objects are, but what they are made of and how they are evolving. The technology behind JWST itself is worth appreciating. The telescope has been in development since the 1990s. It took 25 years and $10 billion to build. Launch was delayed multiple times. Many people thought it would never work. Too complex, too ambitious, too expensive. But it works brilliantly, exceeds design specifications. The mirror is made of 18 hexagonal segments, gold-coated beryllium. Each segment can be adjusted independently to nanometer precision. The entire telescope operates at 40 Kelvin, minus 233 degrees Celsius, colder than outer space naturally is. Requires enormous sun shield. 5 layers of reflective material, each the size of a tennis court, to block heat from sun and earth and moon. The cooling allows infrared detectors to work. Without cooling, their own thermal noise would overwhelm faint signals from distant galaxies. Everything about JWST is at the edge of what is technologically possible, and it is working. Discovering things we did not predict, showing us a universe stranger than we imagined. This is what $10 billion and 25 years of effort and thousands of scientists and engineers working together can achieve. A machine that looks back in time 13.5 billion years and finds impossible galaxies. What happens next with MOMS Z14? More observations. JWST will observe it again. Longer exposures, different instruments, trying to understand the nitrogen anomaly, trying to measure other elements, trying to see if there are multiple stellar populations, trying to determine star formation history. Other telescopes will observe it too. ALMA, the Atacama Large Millimeter Array in Chile, can observe molecular emission, see carbon monoxide and other molecules that trace dense gas where stars form, can measure the dynamics of the galaxy, how fast it is rotating, whether it is merging with other galaxies. Ground-based extremely large telescopes currently under construction, the 30-meter telescope, the Giant Magellan telescope, the extremely large telescope, will eventually observe it with high spectral resolution, measure velocities of individual regions within the galaxy, map the distribution of elements. Each new observation will add pieces to the puzzle. Eventually we will understand MOMS Z14. We'll know whether it is truly anomalous or whether our models need only minor adjustments. We'll know whether nitrogen production in the early universe differs from later epochs. We'll know how common galaxies like this are, but understanding will take time. Years, perhaps decades. Science is slow. Each observation requires telescope time, proposal writing, peer review, observations, data reduction, analysis, publication, debate, more observations. The cycle repeats. Gradually the picture becomes clearer. But we are patient. We have been studying the universe for centuries, can wait years for answers. But while we wait for complete understanding of MOMS 14 specifically, we can already draw broader conclusions. First conclusion: the early universe was more active than we thought. Galaxy formation happened faster. Star formation was more efficient. Chemical enrichment occurred earlier. This means our models need revision, not complete abandonment, but significant modification. Second conclusion: we should be humble about how much we understand. We thought we had a good grasp of galaxy formation, standard model that explained most observations. Then we built a better telescope and found that the model is inadequate at early times. This pattern has repeated throughout history. Every time we improve our instruments, we find surprises, find things that do not fit. This should make us cautious about claiming we understand the universe. We understand the parts we have observed with current instruments. But better instruments always reveal new phenomena, deeper levels of complexity, things we did not predict and cannot yet explain. Third conclusion: the universe is stranger than our theories, more interesting than our models, richer in phenomena than our simulations. This is good news. It means there is always more to discover, always mysteries remaining, always frontier to explore. Science will never run out of questions, never reach complete understanding, because the universe keeps surprising us, keeps revealing complexity we did not anticipate. This is why science is exciting, not because we are close to knowing everything, but because we keep discovering how much we do not know. MOMZ14 is single galaxy, one object among billions, but it represents something larger. It represents the cutting edge of human knowledge. The place where our understanding meets reality and reality says, not quite right. This is where science happens. Not in textbooks, rehearsing established facts, but at the boundary where observations challenge theories, where the impossible forces us to expand our conception of what is possible, where anomalies become opportunities. MOMZ14 tells us that 280 million years after the Big Bang, the universe was already creating complex chemistry, already enriching gas with heavy elements, already forming mature structures, faster than we thought possible. And this raises the question, what else about the early universe is different from our models? What other assumptions are wrong? What other impossible galaxies await discovery? JWST will continue observing. We'll find more anomalies, more impossible objects. Each discovery will refine our understanding, push the boundaries of the possible, show us that the universe is always more complex, more interesting, more surprising than we imagined. This is the gift of impossible discoveries. They force us to think differently, to question assumptions, to expand theories, to recognize that our knowledge is provisional and incomplete, and to keep searching for truth especially when reality contradicts our expectations. This is science at its best. Humble in the face of evidence, willing to revise, eager to discover, accepting that the universe does not conform to our theories but operates according to its own laws which we are still learning to read. MOMZ14 is lesson in humility, and in wonder, and in the inexhaustible strangeness of existence itself. There is something profoundly strange about astronomy that no other science experiences. When you observe a distant galaxy, you are not seeing that galaxy as it is. You are seeing it as it was. Not approximately, not metaphorically, but literally. The light you detect left that galaxy billions of years ago, traveled across space at the speed of light, the fastest speed possible for billions of years before reaching your telescope. During that journey, the galaxy continued existing, evolving, changing. Stars were born and died, gas clouds collapsed and dispersed. Perhaps other galaxies collided with it. Perhaps it merged with neighbors and became something entirely different. Perhaps it was torn apart by gravitational interactions. Perhaps it no longer exists at all in any recognizable form. But you will never see any of this. You can only see the ancient light that is just now arriving. The galaxy you observe is a ghost, a fossil, a memory frozen in light. And this is true for everything in the universe. The sun you see is 8 minutes old. The stars you see at night are years or centuries or millennia old. The Andromeda galaxy you photograph is 2.5 million years old. And MOMZ 14, the impossibly distant galaxy we discussed in part 1, is 13.52 billion years old. We are seeing it as it was when the universe was barely 280 million years old. A toddler. We are looking at the universe's childhood, but that child is now old. That galaxy, if it still exists, is 13.8 billion years old today, nearly as old as the universe itself, completely transformed, and we will never see its present state, never know what it became, because the light showing us its present form will not reach Earth for another 13.52 billion years. Long after the sun has died, long after Earth has been consumed, long after humanity, if it still exists, has moved elsewhere or evolved into something unrecognizable or gone extinct. The present of distant galaxies is inaccessible, hidden, unknowable. We live in a universe where observation is always historical, where the present exists somewhere, but we can never see it, where reality is permanently time-delayed, and the delay increases with distance until it exceeds the age of civilization and approaches the age of the universe itself. Begin with the fundamental limitation, the speed of light. Light travels at 299,792,458 meters per second. This seems fast. In 1 second, light travels far enough to circle Earth 7.5 times. But space is vast beyond comprehension. The sun is 150 million kilometers away. Light takes 8 minutes and 20 seconds to travel from sun to Earth. This means when you look at the sun, do not actually look at the sun. It will damage your eyes. You see it as it was 8 minutes ago, not as it is now. If the sun suddenly vanished, impossible by physics, but hypothetically you would not know for 8 minutes. For 8 minutes, you would see the sun shining normally, feel its heat, experience daylight. Then darkness would arrive, not gradually, all at once. The last photons from the moment before vanishing would arrive. Then no more would follow. Instant night. But for 8 minutes, the Earth would orbit nothing. The sun would be gone, but we would not know. We would be living in the past, responding to information that is no longer current, seeing reality that no longer exists. This becomes more dramatic with greater distances. The nearest star to the Sun is Proxima Centauri. Distance, 4.24 light-years. When you observe Proxima Centauri, you see it as it was 4.24 years ago, not as it is now. The light left the star in early 2022, traveled through space at maximum speed, arrived at Earth in 2026. During those 4.24 years, the star continued existing, rotating, emitting light in all directions, experiencing stellar flares, orbited by its planets. But none of that is visible to you. You see the 2022 version, frozen in time, a photograph from the past displayed in the present. And there is no way to speed this up. No way to see the present version. You must wait. When you observe Proxima Centauri tomorrow, you will see it as it was 4.24 years ago plus 1 day. The delay decreases by 1 day as you move forward in time, but it never catches up. The gap remains. Always 4.24 years. Permanently delayed. Forever historical. Now scale this to the galaxy. The Andromeda galaxy is our nearest large galactic neighbor. Distance, 2.5 million light-years. When you photograph Andromeda, this can be done with commercial telescopes, even high-end cameras with good lenses. You are capturing light that left that galaxy 2.5 million years ago. When that light began its journey, on Earth, Early hominids were just emerging. Homo habilis, using stone tools. No language yet, no art, no civilization. No concept of stars or galaxies or space. Australopithecus still walking the African plains. The entire history of anatomically modern humans the last 300,000 years is just 12% of the time that light has been traveling. The entire recorded history of civilization the last 5,000 years is 0.2% of that light's journey. Everything you know about human existence happened while that light was in transit. And it shows you Andromeda as it was before any of it. Before humans, before Homo sapiens, before civilization, before writing or mathematics or science. The galaxy you observe is profoundly ancient, and the galaxy as it exists now is unknowable. We will not see its current state for another 2.5 million years. If humanity lasts that long, unlikely, given that 99% of all species that have ever existed are now extinct, our descendants might see Andromeda as it was in 2026, might observe events we are contemporary with, but will never see ourselves because they are too far away. And Andromeda is close, cosmologically speaking, a neighbour. Most galaxies are far more distant. The Virgo cluster, a collection of thousands of galaxies, is 50 million light-years away. When you observe it, you see light from 50 million years ago. On Earth, the Eocene epoch, early mammals diversifying. No primates yet, dinosaurs extinct for 15 million years. The entire history of primate evolution happened while that light travelled to us. More distant objects show earlier epochs. Galaxies at 1 billion light-years show the universe as it was 1 billion years ago, before most stars in our galaxy had formed, before the sun existed, before the solar system. We are seeing the past, not metaphorically, not approximately, literally seeing ancient light from ancient times showing us how things were when that light was emitted. And the farther we look, the further back we see. Distance equals time. Looking out equals looking back. Astronomy is inherently historical. We cannot observe the present universe, only the past universe. And the depth of the past increases with distance until we approach the beginning. This is what makes the James Webb Space Telescope so powerful. JWST observes in infrared. Why infrared? Because the universe is expanding. Space itself is stretching. Light traveling through expanding space gets stretched too. Its wavelength increases. This is called redshift. Light that was emitted as visible blue or ultraviolet gets stretched into visible red or infrared. The more expansion occurs during the light's journey, the more it is stretched. The longer the journey, the greater the redshift. The most distant objects have extreme redshift. Their light has been stretched by factors of 10 or 15. What was emitted as ultraviolet arrives as mid-infrared, visible only to infrared telescopes like JWST. Optical telescopes cannot see it at all. This is why JWST can observe objects Hubble could not detect. Not because JWST's mirror is bigger, though it is, 6.5 meters versus Hubble's 2.4 meters, but because JWST sees wavelengths Hubble is blind to. Wavelengths where the most distant and ancient light appears after billions of years of cosmological redshift. Z14 has a redshift of approximately Z equals 14. This means wavelengths are stretched by factor of 15. Light that was emitted at 100 nanometers far ultraviolet arrives at 1,500 nanometers mid-infrared. The galaxy is invisible to optical telescopes, completely. You could point the largest optical telescope on Earth at Z14 and see nothing, darkness, because all the visible light has been stretched beyond the visible range. Only JWST, observing in infrared, can detect it. And what JWST detects is light emitted 13.52 billion years ago, shortly after the Big Bang. when the universe was 280 million years old, just 2% of its current age. We are seeing the universe in its infancy, observing one of the first galaxies to form, watching the cosmic dawn, the era when stars and galaxies were beginning to illuminate space for the first time. This is time travel, one-way time travel. We travel to the past by observing distant objects. The farther the object, the deeper into the past we see. JWST is a time machine, not science fiction, not metaphor. Actually a time machine that lets us observe the universe 13.5 billion years ago by collecting ancient light that has been traveling all that time to reach us now. But here is the disturbing realization. That galaxy MOMZ-14, as it was 13.52 billion years ago, no longer exists, not in that form. It has continued evolving for 13.52 billion years since the light we detect was emitted. Those 13.52 billion years are nearly the entire age of the universe. 98% of cosmic history has elapsed since we saw it. During that time, the galaxy has changed utterly. The stars we see as newborn have long since died. Multiple generations of stars have formed and exploded. The gas has been enriched with heavy elements. The structure has evolved. Spiral arms may have formed, or the galaxy may have collided with neighbors. Mergers are common. Small galaxies frequently merge to form larger galaxies. The Milky Way is currently absorbing several small galaxies. In 4 billion years, Andromeda will collide with the Milky Way, and the two will merge into elliptical galaxy. This is the fate of many galaxies. MOMZ-14, being small and in the early universe where galaxies were closer together, almost certainly merged with other galaxies. Perhaps many times. Perhaps it is now part of a massive elliptical galaxy. Perhaps it lost its identity entirely, its stars scattered among many successor galaxies. We do not know. We cannot know. Because we can only see the past. The present is hidden. What is MOMZ-14 doing right now? Not 13.52 billion years ago, but now. At this instant, the answer is, we will never know. And right now is not even well defined at such distances. In relativity, simultaneity is relative. Different observers disagree about what events are simultaneous. There is no universal now that applies everywhere in the universe. An observer on Earth and an observer in MOMZ-14 would have different notions of now. The faster you move, the more your time axis tilts relative to someone at rest. At cosmological distances, the concept of now becomes ambiguous. But even setting aside relativistic complications, even if we define now as the time at MOMZ-14, that is 13.8 billion years after the Big Bang, the same age as the universe at our location, we can never observe it. The light from MOMZ-14's present state has not reached us yet. It is en route, traveling through space at the speed of light. Will arrive in 13.52 billion years. Long after the Sun has become a red giant and engulfed the Earth. Long after the Sun has become a white dwarf and faded, the present of MOMZ-14 is inaccessible to us. We are trapped in observing only its past, permanently, inescapably. This creates a strange kind of loneliness. We are surrounded by reality we cannot see. The present universe exists, trillions of galaxies, each doing something right now. Stars forming, stars exploding, planets orbiting, perhaps civilizations existing, perhaps technologies operating, perhaps beings looking back at us through their telescopes, observing the Milky Way as it was billions of years ago, wondering if anyone is here. But we cannot see them now, can only see their pasts, and they can only see our past. The present is fragmented, shattered by the speed of light into unreachable pieces scattered across space. We share the universe with countless other galaxies, but never share the present with them. always separated by light travel time, always looking at each other's history rather than each other's now. This is the speed of light limit, the cosmic speed limit that prevents faster communication, prevents simultaneity, isolates each location in its own light cone. You can only see the past light cone, everything from which light has had time to reach you. You cannot see outside your light cone, cannot see events that are too far away for light to have arrived yet, cannot see the present of distant places, only the past. But it is worse than that. Even nearby objects we observe in the past. Your friend standing across the room, the light from their face takes a nanosecond to reach your eyes. You see them as they were a nanosecond ago, not as they are now. The delay is negligible, unmeasurable, in ordinary experience. But it is real. You never see the present, not even of objects right in front of you. Always there is delay. Light takes time to travel, and observation requires light. So observation is inherently delayed, inherently historical. The now you perceive is always slightly past. For distant objects, the delay is significant. For extremely distant objects, the delay is longer than the history of human civilization. For the most distant objects we can observe, the delay approaches the age of the universe. We are seeing the universe shortly after its birth, and that birth is now 13.8 billion years in the past. The universe has grown old, has evolved, has changed beyond recognition in many ways, but we can still see its childhood by looking far enough. This is the magic of astronomy and the tragedy. Magic, because we can observe the universe's history, see how it evolved, watch galaxies forming, stars igniting, structure emerging from primordial chaos. Tragedy, because we can never see the present, never know what became of those early galaxies, never catch up to the present state of the universe we observe in the past. Consider the implications for the search for extraterrestrial life. SETI, the search for extraterrestrial intelligence, looks for radio signals from alien civilizations. Radio waves travel at the speed of light. If we detect a signal from a star 1,000 light years away, that signal was transmitted 1,000 years ago, on Earth the year 1026, before the Norman conquest of England, before the Crusades, before gunpowder. The civilization that sent the signal might no longer exist. Perhaps they destroyed themselves in war. Perhaps a natural disaster wiped them out. Perhaps they evolved into something unrecognizable. Perhaps they are still there, much more advanced than when they sent the signal. But we would not know. We would be detecting their past. And if we sent a reply, it would take 1,000 years to reach them. And their response would take another 1,000 years to return to us. A round-trip conversation would take 2,000 years. Empires rise and fall in less time. Civilizations disappear. Humanity might not exist in 2,000 years. The signal we send might arrive at a dead world, or the response might arrive at a dead Earth. Communication across interstellar distances is not just difficult because of the distances. It is difficult because of time delay. The conversation happens across centuries or millennia. You send a message to the past. You receive messages from the past. The present is never synchronized. The speed of light prevents simultaneity, turns interstellar communication into dialogue with ghosts. This applies to observation too. If we detect biosignatures in the atmosphere of an exoplanet 100 light-years away, oxygen or methane, indicating possible life, we are detecting life as it was 100 years ago. The planet might be lifeless now, or the life might have evolved, or gone extinct, or developed technology. We do not know. We see only the past, and this asymmetry is permanent. We can never observe the present of distant objects, can only infer, can model, can predict, but cannot directly observe. The present exists, but is hidden behind the speed of light barrier. Observable only to those within light travel time. For extremely distant objects, the barrier is insurmountable. We will never see their present, never close the gap. Because the gap is 13.52 billion years, and we do not have 13.52 billion years. The sun will die first. Humanity will be gone. The Earth will be gone. By the time the present-day light from MOMSI 14 reaches the location where Earth once was, there will be no one to observe it. The observation is impossible. Not just difficult, impossible. Forbidden by time and mortality and the vastness of space. Yet we continue observing, continue building telescopes, continue looking deeper into space and therefore deeper into time. Why? Because the past is accessible even if the present is not, and the past is rich with information. By observing many galaxies at many distances, we see the universe at many different ages. We see galaxies as they were 1 billion years ago, 5 billion years ago, 10 billion years ago, 13 billion years ago. By comparing them, we reconstruct the history of galaxy evolution. We see young galaxies and old galaxies and everything in between. We cannot watch a single galaxy evolve that would require waiting billions of years. But we can watch the population of galaxies evolve by observing representatives from each epoch. This is like studying human development by observing many individuals of different ages. You cannot watch one person grow from infant to adult in real time. That takes decades. But you can observe infants and toddlers and teenagers and adults simultaneously and infer the developmental trajectory. Astronomy does this with galaxies, observes the past, samples many times, reconstructs evolution, and it works. We have learned enormous amounts about how galaxies form and evolve by observing them at different distances and therefore different ages. This is the power of looking back. Even though we cannot see the present, we can see the past. And the past tells us how the present came to be. MOMSI 14 is one snapshot, one moment in one galaxy's history, 280 million years after the Big Bang, just starting to enrich with heavy elements, just beginning to form complex chemistry. It tells us what galaxies were like in the cosmic dawn, what conditions were like, what processes were operating. And when we find anomalies like the excess nitrogen, we learn that our models are incomplete. That something about the early universe was different from what we thought. The observation forces us to refine theories, to look more carefully, to observe more galaxies at that epoch, to build statistics, to determine whether MOMSI 14 is unusual or typical. And eventually we will understand. We'll know why nitrogen is overabundant. We'll know how galaxies enrich themselves so quickly. We'll have a better model of the early universe. But we will still be looking at the past, still unable to see the present. That limitation is permanent, built into the structure of space-time. Light speed is not just a speed, it is the speed at which causality propagates, the speed at which information can travel, the speed at which the future becomes the past, and it is finite, not infinitely fast, which means there are regions of space whose present we can never see, regions beyond our cosmological horizon, so far away that light from them has not had time to reach us yet. These regions might as well not exist for us. We cannot observe them, cannot interact with them, cannot know anything about them. They are causally disconnected from us, outside our observable universe. The observable universe has a radius of about 46 billion light-years, not 13.8 billion light-years as you might expect from the age of the universe. The discrepancy is because space itself has been expanding. Light travels through expanding space. By the time it reaches us, the source has moved farther away. The most distant objects we can see are now 46 billion light-years away, even though the light took only 13.8 billion years to reach us. But there is more universe beyond. The universe is likely infinite, or at least much larger than the observable part. But we can only see the observable part, only 46 billion light-years in any direction. Beyond that, is unknown. Perhaps other galaxies, perhaps other structures, perhaps nothing. We cannot know, cannot observe, cannot detect. It is outside our light cone, outside our causal contact, permanently inaccessible. We live in an island of observability, surrounded by an ocean of the unobservable. And the island is not even the present, it is the past. The observable universe is a sphere of past light cones. Everything in it is historical. Nothing in it is present. We live in a bubble of the past, surrounded by an unknowable present that exists beyond our reach. This is humbling. We think of ourselves as observers of the universe, but we observe only a tiny fraction of the universe, the observable part. And even that, we observe only in the past. The present universe is vastly larger than the observable universe, and we can never see it, can never know its full extent, can never determine what lies beyond our cosmological horizon. Perhaps infinite galaxies, perhaps different physics, perhaps regions where constants are different, perhaps the universe is different out there in ways we cannot imagine because we cannot observe it. This is the ultimate limit of empirical science. We can only study what we can observe, and observation is limited by the speed of light and the age of the universe. Beyond those limits, we can speculate, can theorize, can model, but cannot test, cannot confirm, cannot know with certainty. The universe keeps secrets, hides most of itself from us, shows us only the past of the observable part, and even that past is incomplete because we can only detect light and other electromagnetic radiation, neutrinos, gravitational waves. But most of the universe, dark matter and dark energy, is invisible to all our instruments. We infer it from gravitational effects, but cannot observe it directly. So even the past we observe is incomplete, shows us only the luminous matter, the stars and gas, not the dark matter that dominates, not the dark energy that accelerates expansion. We are blind to 95% of the universe's contents, and we are delayed by billions of years from seeing the present. We observe a small, historical, incomplete sample of reality, and from that sample we try to understand everything. It is remarkable that we succeed at all, that we have learned as much as we have given such severe limitations. Yet we persist, build bigger telescopes, observe fainter objects, look deeper into the past, and keep discovering. Keep finding things that do not fit our models. Keep being surprised. MOMZ14 surprised us with its nitrogen. Other galaxies surprise us with their masses, with their maturity, with their abundance at early times. Each surprise refines our understanding. Each anomaly forces us to think harder, to question assumptions, to revise theories. This is the scientific method. Observe, hypothesize, test, revise, repeat. It never ends. Because the universe is more complex than any theory can fully capture. Always there are new phenomena, new scales, new regimes where old rules break down and new rules emerge. We discover these by pushing boundaries, by looking farther, by observing more carefully, by building instruments that extend our senses beyond their natural limits. Telescopes extend our vision across billions of light years. Spectrographs let us analyze chemical composition of objects we can never touch. Interferometers measure positions to milliarc-second precision. We have become very good at observing the past, at extracting information from ancient light, at reconstructing history from fossils of photons that have traveled across the universe to reach us. This is our strength, our capability, our triumph. We look at the past and we see clearly. We measure, we analyze, we understand. But the present remains hidden, remains unknowable, remains forever out of reach no matter how clever our instruments or how patient our observations. The present of MOMZ14 is lost to us, not because we lack technology, but because it is too far away. The information has not arrived yet, will not arrive for billions of years, by which time we will be long gone and there will be no one left to receive it. The message is sent, the light is traveling, but the recipient will never exist to read it. This is the tragedy of cosmic distance. The present is always elsewhere, always unreachable, always beyond the horizon of what we can know. We are archaeologists of light, studying relics from the deep past, inferring history from fragments, building narrative from incomplete evidence, and doing remarkably well. But we are not observers of the present. We are students of history, looking back, always back, into depths of time so vast that civilizations rise and fall in the blink of an eye by comparison. MOM-Z14 is not a galaxy, it is a memory, a fossil, a monument to what was, and what was is gone, transformed, evolved into something we will never see. This is astronomy, the science of studying things that no longer exist as we observe them, the science of the forever past, the science of distant ghosts. It is beautiful, it is profound, it is all we have, and it is enough, because even the past, even incomplete, even delayed by billions of years, tells us truths about the universe and our place in it, tells us we are latecomers, observers of ancient light, witnesses to history so deep that our entire species is a footnote in cosmic time. And yet we look, and yet we wonder, and yet we discover. This is what makes us human. The drive to know even what we can never fully reach. The curiosity that compels us to build telescopes and point them at the darkness and wait patiently for ancient photons to arrive, carrying news from the impossible past, from the galaxies that were and are no more, from the universe as it was at the beginning, before us, before anyone, when only physics operated and chance and necessity shaped stars from gas and galaxies from stars and complexity from simplicity across billions of years that we can observe but never visit, never change, never reach, only remember through the light that remains. This is part 2 of the impossible galaxy, the galaxy that exists in our observations but nowhere in present reality, the galaxy that is and is not, that was but is no more, that we see but cannot touch, that teaches us about the past and reminds us of our limits, of the vast gulf between what is and what we can know, of the permanent delay between reality and observation that no technology can overcome because it is woven into the fabric of space-time itself. We look back 13.5 billion years and see MOM-Z14, and MOM-Z14 looks back at us across the same gulf and sees the Milky Way as it was 13.5 billion years ago, long before the Sun formed, long before the Earth existed, long before life or consciousness or questions arose about the nature of distant light and the galaxies it reveals, and the pasts it preserves, and the presents it hides, and the futures it cannot show. This is our situation. This is our limit. This is the universe we inhabit. Forever historical, forever delayed, forever reaching toward a present we can never grasp. There is a pattern in the history of science that repeats with uncomfortable regularity. A generation of scientists develops a theory. The theory explains observations beautifully. Predictions match experiments. The mathematics is elegant. Textbooks are written. Students are taught that we understand how nature works. The scientists grow confident. Some even declare that physics is nearly complete, that only minor details remain to be worked out, that the fundamental laws are known and future work will merely refine measurements and apply known principles to new situations, and then someone builds a better instrument, or makes a more careful observation, or looks at something no one thought to examine before, and they find something impossible, something that does not fit the theory, something that contradicts established understanding, an anomaly, At first, the anomaly is dismissed. Measurement error, perhaps, or misinterpretation. The theory has worked so well for so long that surely this one strange result is wrong. But the observation is repeated, confirmed, extended, and eventually it becomes undeniable that the theory, the beautiful, elegant, well-tested theory, is wrong. Not completely wrong. It still works in the regimes where it was tested, but it is incomplete. There are phenomena it cannot explain, domains where it breaks down, new physics lurking beyond the boundary of previous observations. This has happened over and over throughout history. Newtonian mechanics was perfect until Mercury's orbit did not quite fit, until the speed of light refused to change no matter how you moved. Then came relativity. Thermodynamics was complete until blackbody radiation curves diverged at short wavelengths, until atomic spectra showed discrete lines instead of continuous emission. Then came quantum mechanics. The Big Bang model was settled until galaxies were found rotating too fast, until the universe was measured to be accelerating instead of decelerating. Then came dark matter and dark energy. Every generation thinks it has nearly solved physics. Every generation is proven wrong, and the James Webb Space Telescope is doing it again, showing us galaxies that should not exist. Structures too mature too early, chemical enrichment too fast, too many massive galaxies in the early universe. The standard model of galaxy formation, lambda CDM cosmology combined with hierarchical structure formation, does not predict what JWST observes. Something is wrong with our understanding, again, and this should not surprise us. This is how science works. This is how knowledge advances, not smoothly, not by gradually filling in details of a complete picture, but by encountering failures, by finding the impossible, by being forced to admit that what we thought we knew was incomplete or incorrect, and then building better theories that explain both the old observations and the new impossible ones. This is progress, painful progress, humbling progress, but progress nonetheless. Begin with historical examples. Isaac Newton published Principia Mathematica in 1687. It contained his laws of motion and universal gravitation. These laws explained everything: terrestrial motion, planetary orbits, tides, comets. Everything that moves obeys Newton's laws. For 2 centuries, Newtonian mechanics was the foundation of physics. Extraordinarily successful. Predictions matched observations to high precision. Engineers used Newton's laws to build machines. Astronomers used them to predict planetary positions decades in advance. The predictions were accurate. The theory worked, but there were small anomalies. Mercury's orbit, for example. Mercury is closest planet to the Sun. Its orbit is elliptical, like all planets, but the ellipse itself rotates slowly. The perihelion, the point of closest approach to the Sun, advances around the Sun. This is called perihelion precession. Most of Mercury's precession is caused by gravitational tugs from other planets. Jupiter, Venus, Earth all pull on Mercury. Their gravitational influences cause the orbit to precess. Astronomers calculated how much precession should occur from planetary perturbations using Newtonian gravity. The calculation was careful, detailed, and when compared to observations, there was a discrepancy. Mercury's perihelion was precessing 43 arc-seconds per century faster than Newtonian gravity predicted. This is tiny. 43 arc-seconds is about 0.012 degrees per century. Barely detectable, but it was real, confirmed by multiple observers, and no one could explain it using Newtonian physics. Some astronomers proposed an undiscovered planet closer to the Sun than Mercury. They named it Vulcan, searched for it, never found it, because it does not exist. Others proposed modifications to Newton's law of gravity, adding extra terms, adjusting the exponent in the inverse square law. But these modifications were ad hoc, invented to fix one problem without clear physical justification, and they failed to work in other contexts. The discrepancy remained, a small thorn in the side of Newtonian mechanics, ignored by most physicists because it was so small and everything else worked so well. Then in 1915, Albert Einstein published general relativity, a completely new theory of gravity, not a force, but curvature of space-time. Mass and energy curve space-time. Objects move along straightest possible paths through curved space-time. These paths appear curved in our perception, which we interpret as gravitational attraction. The mathematics is complex, tensor calculus, non-linear equations. But the predictions are testable. And one of the first tests was Mercury's orbit. Einstein calculated what general relativity predicts for Mercury's perihelion precession. The calculation took into account the curvature of space-time caused by the Sun's mass, and the result was exactly 43 arc-seconds per century more than the Newtonian prediction, exactly the observed discrepancy, with no adjustable parameters, no fudge factors, just the theory applied straightforwardly. Einstein later said this was one of the happiest moments of his life. The theory explained the anomaly perfectly. Mercury's orbit was not impossible. It was exactly what general relativity predicted. Newtonian gravity was wrong. Not completely wrong. It works fine for weak gravitational fields, but incomplete. There is a deeper theory. And the anomaly, the impossible observation that did not fit the old theory, pointed the way. Or consider the ultraviolet catastrophe. In the late 1800s, physicists studied black body radiation. Any object with temperature emits electromagnetic radiation. The spectrum, the intensity at different wavelengths, depends on temperature. Hotter objects emit more radiation, and at shorter wavelengths. This is why hot metal glows red, then orange, then white as it heats up. Physicists tried to derive the blackbody spectrum from fundamental principles using classical physics, thermodynamics, and electromagnetism. The calculation predicted that intensity should increase without limit as wavelength decreases, that infinite energy should be radiated at ultraviolet and shorter wavelengths. This is the ultraviolet catastrophe. Obviously wrong. Real objects do not emit infinite energy. The observed spectrum peaks at some wavelength and decreases at both longer and shorter wavelengths. But classical physics could not explain this. The theory predicted the impossible. Then in 1900, Max Planck found a formula that fit the data perfectly. But to derive it, he had to make a strange assumption. He assumed energy is quantized, that electromagnetic energy comes in discrete packets quanta rather than continuous amounts. The energy of each quantum is proportional to frequency, E equals hf, where h is Planck's constant. This assumption had no justification in classical physics. It was purely empirical, invented to make the math work. But it worked. The Planck blackbody formula matches observations exactly, and the quantization assumption led eventually to quantum mechanics, a complete revolution in physics, all because the classical theory failed, because observations showed something impossible according to established understanding. The anomaly forced new physics, or the expansion of the universe. Einstein's general relativity, when applied to the universe as a whole, predicts that the universe cannot be static. It must either expand or contract. Gravity pulls matter together. Without some counteracting force, the universe should collapse. Einstein did not like this. He believed the universe was static, eternal and unchanging. So he added a term to his equations, the cosmological constant that acts as repulsive force at large scales. This term allowed static solutions. balanced gravitational attraction with cosmic repulsion. Einstein thought this was necessary, thought the universe must be static. Then, in 1929, Edwin Hubble measured the spectra of distant galaxies. He found that almost all galaxies are redshifted. Their light is shifted toward longer wavelengths. The farther the galaxy, the greater the redshift. Hubble interpreted this as Doppler shift. Galaxies are moving away from us, and the relationship is linear. Velocity proportional to distance. This is exactly what you expect if the universe is expanding uniformly. All galaxies moving away from each other. Space itself stretching, carrying galaxies along. Einstein reportedly called the cosmological constant his biggest blunder. He had the correct equation. General relativity naturally predicts expansion, but he modified it to force a static solution because he thought the universe must be static. Then observations proved the universe is not static. The theory was right. Einstein's philosophical prejudice was wrong. This is a slightly different lesson. Sometimes the theory is correct, but we misapply it because we assume things about reality that are not true. We think the universe should be static, or we think particles should have definite positions, or we think time should be absolute. And we modify theories or reject predictions to preserve these intuitions. Then observations show our intuitions are wrong. Reality does not care what we think it should be. It is what it is. And our job is to adjust our thinking to match reality, not to adjust reality to match our thinking. Fast forward to the 1970s. Astronomers were measuring rotation curves of spiral galaxies. A rotation curve shows how fast stars and gas orbit the galactic center as a function of distance from the center. In the solar system, planets farther from the sun orbit slower. This is Kepler's law, follows from Newton's gravity. You expect the same in galaxies. Stars near the center orbit fast. Stars far from the center orbit slower. But observations showed something different. Stars in the outer regions of galaxies were orbiting just as fast as stars closer to the center. The rotation curve was flat instead of declining. This is impossible according to visible matter distribution. The gravity from visible stars and gas is not enough to hold the outer stars in such fast orbits. They should fly away, escape the galaxy, but they do not. Astronomers checked their measurements, repeated observations, different galaxies, same result, flat rotation curves everywhere. Then Vera Rubin and Kent Ford made extremely careful measurements, state-of-the-art instruments, rigorous analysis, confirmed the flat rotation curves beyond doubt. The conclusion was inescapable. Either Newton's laws of gravity are wrong at galactic scales, or there is more mass in galaxies than we can see. Most astronomers accepted the second option, dark matter, invisible matter that does not emit light, cannot be detected directly, but has gravity. If galaxies contain much more mass than the visible stars and gas suggest, if perhaps 85% of the mass is dark, then the rotation curves make sense. The gravity from the dark matter holds the visible matter in fast orbits. This seemed absurd at first, invoking invisible, undetectable matter to save the theory, but additional evidence accumulated. Gravitational lensing, colliding galaxy clusters where the mass is separated from the visible matter, cosmic microwave background fluctuations that require dark matter to explain. The evidence became overwhelming. Dark matter is real. We do not know what it is, probably some exotic particle that does not interact electromagnetically, but it constitutes 85% of all matter in the universe. Ordinary atoms, protons, neutrons, electrons, are only 15% of the matter. We are the minority, made of rare stuff. Most of the universe is something else, something dark, something we still do not understand despite decades of searching. Then, in 1998, even stranger discovery, two independent teams measuring distances to distant supernovae found that the universe's expansion is accelerating, not slowing down as expected. After the Big Bang, the universe began expanding. Gravity should slow the expansion, eventually halt it and cause recollapse. Or if there is not enough matter, expansion should continue forever but decelerating. These were the two possibilities, but observations showed neither. Expansion is speeding up. Galaxies are moving apart faster and faster. This requires some kind of repulsive force, some form of energy that fills space and pushes everything apart. Dark energy, even more mysterious than dark matter. Dark energy constitutes about 68% of the total energy of the universe. Dark matter is 27%. Ordinary matter atoms is only 5%. We do not know what dark energy is. Best candidate is the cosmological constant. The term Einstein added, and later regretted. Turns out it might be necessary after all. But we do not understand why it has the value it does, why it is not zero, why it is not vastly larger. Quantum field theory predicts it should be 120 times larger than observed. This is the worst prediction in the history of physics, off by 120 orders of magnitude. We have no explanation. Dark energy is complete mystery, yet it dominates the universe. Determines the ultimate fate, will cause galaxies outside our local group to eventually disappear beyond the cosmic horizon as space expands faster than light can travel. We live in a universe where 95% of the contents dark matter plus dark energy are completely unknown. We know they exist from gravitational effects, but we do not know what they are, cannot detect them directly, can only infer them indirectly. This is humbling. We understand only 5% of the universe. The normal matter, atoms and molecules, chemistry and nuclear physics, the stuff we are made of. But this is a tiny fraction of reality. The universe is mostly something else, something dark, something beyond our current physics to explain. Now the James Webb Space Telescope is finding problems with galaxy formation. The standard model lambda CDM cosmology assumes dark matter is cold, moves slowly, clumps under gravity to form halos. Baryonic matter, ordinary atoms, falls into these halos, cools, forms stars. Small galaxies form first, merge over time to form larger galaxies. This is hierarchical structure formation, predicted by computer simulations. Should produce universe where small galaxies are common early and large galaxies form later. But JWST observes massive galaxies at z equals 10, z equals 11, z equals 12, z equals 14. Less than 500 million years after the Big Bang. These galaxies contain billions of solar masses of stars. This is too much too fast. Simulations do not predict this. Either star formation was much more efficient in the early universe than we model, or dark matter behaves differently than we assume, or there are feedback mechanisms we do not understand that trigger rapid galaxy growth. Or our entire model of structure formation is missing something fundamental. We do not know which, but something is wrong. The observations are inconsistent with predictions. This is being called the JWST crisis in cosmology. Not crisis because JWST is wrong. Crisis because our theories are inadequate. Cannot explain the data. Need revision. Perhaps major revision. This is where we are now. Facing anomalies again. Impossible galaxies. Just like Mercury's impossible orbit. Like the ultraviolet catastrophe. Like dark matter and dark energy. Every generation faces these challenges. Every generation thinks they nearly understand everything. Every generation is proven wrong. And this is good, because it means there is more to discover, more to learn. The universe is not exhausted, not fully mapped, not completely understood. There are frontiers, there are mysteries, there are phenomena beyond our current theories, and finding them drives progress. forces creativity, requires new ideas. This is how science advances, not by confirming what we already believe, but by finding where our beliefs fail, where reality deviates from theory, and then building better theories that explain both the old observations and the new anomalies. This process never ends, because the universe is more complex than any finite theory can capture. Always there are new scales, new energies, new distances, new phenomena that emerge in regimes we have not yet explored. And when we explore them, we find surprises, find things that do not fit, find the impossible, and we revise, again and again, forever. What else do we not understand? The list is long. We do not understand what dark matter is. Despite decades of searching, no experiment has detected dark matter particles directly. We have ruled out many candidates, but the right answer remains hidden. We do not understand what dark energy is, whether it is cosmological constant or something more complex, whether it is constant over time or evolving. We do not understand what happened before the Big Bang, whether the question even makes sense, whether time itself began at the Big Bang or whether there was something before. We do not understand why the universe has the physical constants it does, why the speed of light is 299,792,458 meters per second rather than some other value, why the electron has the mass it has, why the fine structure constant is 1/137. These are measured values, inputs to our theories, not derived from deeper principles. We do not understand why there is more matter than antimatter. The Big Bang should have created equal amounts. They should have annihilated, leaving only radiation, but some matter remained, a tiny asymmetry, 1 part in a billion, just enough to create all the stars and galaxies. We do not know why. We do not understand quantum mechanics, not fully. We can calculate, can predict, can match experiments to extraordinary precision, but we do not understand what the wave function represents, whether collapse is real or apparent, whether many worlds exist or just one, whether hidden variables might restore determinism. The measurement problem remains unsolved after a century. Interpretations multiply. Experiments cannot decide between them because they make identical predictions for all measurable quantities. We do not understand how to unify quantum mechanics and general relativity. They are both correct in their domains, but incompatible. Quantum mechanics describes the small. General relativity describes the large. At the intersection quantum gravity, we have no working theory. String theory is candidate, loop quantum gravity is another, but neither is confirmed experimentally. Both are speculative. We do not know which, if either, is correct. We do not understand consciousness, how subjective experience arises from physical processes. The hard problem. Why there is something it is like to be conscious. We can study neural correlates, can identify brain regions involved, can even manipulate consciousness through drugs or stimulation. But we cannot explain why any of this produces subjective experience rather than just unconscious information processing. This might be the deepest mystery of all. We do not understand whether we are alone, whether life exists elsewhere, whether intelligence is common or rare, whether civilizations typically destroy themselves or survive to spread across galaxies. We have found thousands of exoplanets, some in habitable zones, some with atmospheres, but no confirmed biosignatures yet, no signals from alien civilizations. Either we are alone, which seems unlikely given the vast number of planets, or intelligent life is rare or short-lived or quiet or uninterested in communication or using technologies we cannot detect. We do not know. We do not understand the origin of life, how chemistry becomes biology, how non-living molecules organize into self-replicating systems, how metabolism and genetics and cellular structure emerge. We have hypotheses, RNA world, hydrothermal vents, panspermia, but no confirmed mechanism. Cannot create life in the laboratory from non-living precursors. Cannot identify the specific pathway that led from chemistry to biology. This is fundamental question. How does life begin? And we do not have the answer. We do not understand the ultimate fate of the universe. Will expansion continue forever? Will dark energy remain constant or change? Will the universe eventually reach heat death, maximum entropy, no gradients, no structure, just diffuse radiation approaching absolute zero temperature? Or will something else happen? Will dark energy decay? Will new fields activate? Will quantum tunneling trigger vacuum decay that destroys everything? We can model scenarios, but we cannot predict with certainty because we do not understand dark energy. We do not understand whether the universe is finite or infinite, whether it has boundaries or extends forever, whether other universes exist, whether there is multiverse. These are open questions, deep questions, and we have very limited ability to answer them because observation is constrained by light cones and cosmic horizons. Much of reality is inaccessible, hidden beyond the observable universe, permanently out of reach. We can speculate but cannot confirm. What is the lesson of all this ignorance? Not despair, not nihilism, but humility. We know some things. Physics works remarkably well in tested domains. We can predict planetary positions centuries in advance, can calculate energies of nuclear reactions, can design transistors and lasers and GPS satellites. Our theories work, but they are limited, incomplete, work in certain regimes, break down in others. We know 5% of the universe's contents. Ordinary matter, atoms and light. The rest, dark matter, dark energy, is unknown. We can observe back to 380,000 years after the Big Bang, using cosmic microwave background. But earlier times are opaque. We can see out to 46 billion light years, but beyond is unobservable. We can measure down to Planck scale in principle, but below that, quantum gravity takes over and we have no theory. We operate within boundaries, within limits, and constantly we push against those limits. Build bigger telescopes, higher energy colliders, more sensitive detectors, trying to expand the known, trying to probe the unknown, and every time we do, we find surprises. Find things that do not fit our models. Find the impossible, and we adjust. Revise theories, build better models, and then push further, and find new impossibilities. This cycle never ends. This is science. Permanent revolution, continuous discovery, endless confrontation with our own ignorance. And this is good, because it means the universe is inexhaustible. No matter how much we learn, there is more. New scales, new phenomena, new mysteries. We will never reach the end. We'll never know everything. This is not failure. This is the nature of reality. The universe is complex, beyond imagination, rich in structure, deep in layers. Each answer generates new questions. Each solved mystery reveals deeper mysteries. This is not discouraging. This is exciting. It means science will never become obsolete, will never run out of problems, will always have frontiers, will always need explorers, will always reward curiosity. The universe invites investigation, rewards persistence, punishes arrogance, humbles the certain, empowers the curious, and shows us over and over that reality is stranger than our theories, more wonderful than our models, more surprising than we can anticipate. MOM-Z14 is one example, one impossible galaxy, but it represents larger truth. That observation always runs ahead of theory, that nature is more creative than physicists, that the universe does not care what we think is possible. It does what it does, and our job is not to dictate to nature but to listen, to observe carefully. to measure precisely, to think deeply, and to remain humble, because every generation that claimed to nearly understand everything was proven wrong. And we are no different. We know more than previous generations, but we are also wrong about things. Current theories are incomplete. There are anomalies we have not yet found, phenomena we have not yet observed, physics beyond our current understanding, and the next generation will find them. We'll build better instruments, we'll observe more carefully, we'll discover things we cannot imagine, and they will look back at us and smile, at our confidence, at our incomplete theories, at our limited understanding, just as we look back at Newton, thinking gravity is force, at Einstein rejecting quantum mechanics, at every generation that thought they were near the end and turned out to be at the beginning. This is the human condition in science. Perpetual students, forever learning, never graduating. Because the universe is the teacher and the curriculum is infinite. So when we find impossible galaxies like MOMSI 14, we should not be surprised, should expect this, should welcome it, because it means we are still learning, still discovering, still at the frontier where observation challenges theory, where reality exceeds imagination, where the universe reveals itself to be more than we thought, more complex, more interesting, more beautiful. This is the gift of anomalies. They keep science alive, keep it honest, keep it progressing. Without anomalies, science would stagnate, would become dogma, would stop questioning, would calcify into rigid belief system. But anomalies prevent this. Keep forcing revision, keep demanding new ideas, keep showing that we do not have final answers, only provisional answers, good enough for now, but subject to revision, subject to improvement, subject to being overturned, when better observations reveal deeper truth. This is not weakness, this is strength, the ability to admit error, to revise belief, to follow evidence even when it contradicts expectation. This is what makes science powerful, not that it is always right, but that it can correct itself, can improve, can converge toward truth through iterative process of hypothesis, test, revision, repeat. Other systems of knowledge claim certainty, claim final truth, claim answers that cannot be questioned. Science claims only provisional understanding, best current model, subject to change. And this humility, this willingness to be wrong, is precisely what allows science to be right more often over time, because reality is the final arbiter, not authority, not tradition, not sacred texts. Reality, observation, evidence, what actually happens when you do the experiment, when you make the measurement, when you point the telescope and collect the photons. And if reality contradicts theory, theory must change, not reality. This is the scientific method, and it works, slowly, imperfectly, with many false starts and dead ends. But it works. It produces knowledge that is reliable within tested domains, and it identifies boundaries beyond which knowledge is uncertain. This combination, reliable knowledge within limits, plus honest acknowledgement of limits, is science's great strength. We know what we know what we do not know, and we admit the difference. MOMSI 14 reminds us of how much we do not know, of how early the universe is surprising us, of how our models fail to predict what is actually observed. This is uncomfortable, challenges, confidence, forces reassessment, but it is necessary, because being wrong is how we learn we are wrong, and knowing we are wrong is first step toward being less wrong. Science does not provide truth with capital T. It provides increasingly accurate approximations to truth, models that work better than previous models, theories that explain more than previous theories. Each generation builds on previous generations, stands on shoulders of giants, and sees further, understands more deeply, but never reaches absolute, complete, perfect understanding, because the universe is too rich, too complex, too deep. We can spend millennia studying it and still find new phenomena, new scales, new mysteries. This is cause for joy, not despair. It means the adventure continues. The quest never ends. The frontier remains. Always, there is more to explore, more to discover, more to understand. And every discovery, even when it shows we were wrong, brings us closer to truth, closer to understanding, closer to seeing reality as it is rather than as we imagine it. This is the goal, not to confirm what we believe, but to discover what is true regardless of what we believe. And the universe is generous with surprises, with anomalies, with impossible observations that force us to revise, to expand, to deepen our understanding. Mom Z14 is gift, wrapped in impossibility, teaching us that we have more to learn, that galaxy formation is not fully understood, that the early universe was different than we modeled, that nitrogen forms faster than we thought, that complexity emerges sooner than predicted. These are lessons, opportunities, invitations to think harder, to observe more, to revise theories, and to remain humble, because the universe is vast and we are small. The universe is ancient and we are young. The universe is complex and we are limited, but we are curious and we are persistent, and we are capable of learning, of discovering, of understanding incrementally, bit by bit, discovery by discovery, anomaly by anomaly, building knowledge that is partial but real, incomplete but useful, provisional but powerful. This is science. This is humanity's great cognitive achievement, the ability to study reality systematically, to test ideas empirically, to revise beliefs based on evidence, to accumulate understanding across generations, and to do all this while remaining humble about how much remains unknown, how much the universe still hides from us, how many mysteries remain unsolved, how many impossible discoveries await those who have courage to look, to observe, to question, to wonder. This is the spirit that built JWST, that pointed it at ancient light, that found Mom Z14, that discovered the impossible, and that will continue discovering, continue questioning, continue learning, forever. Because the universe is infinite teacher, and we are eternal students, and the curriculum never ends, but only deepens and expands with each generation that takes up the quest to understand existence itself. This is part 3. The part about not knowing, about being wrong, about staying humble, about embracing mystery, about celebrating impossibility. Because impossible things are where discovery happens, where science lives, where understanding grows, at the boundary between the known and unknown, where Mom Z14 waits, impossible, real, teaching us, challenging us, reminding us that we have only begun to understand this strange, beautiful, impossible universe we inhabit.